Well, I decided in the end to put a video together for the November 2016 paper, so do it again, sort of 4 rounds of 10 questions. First video, turn over, because we've got a trusty periodic table, that's all we get in the exam, not the data booklet, and it's in kind of the order that it's taught in topic number, so calculations first, then atomic structure, then periodicity, and so on. So we start off with the calculations, not all calculations. Don't forget, of course, you don't get a calculator, so you're only working on your mental arithmetic. So question number 1, what volume in centimetres cubed of 0.2 mole per decimeter cubed sodium hydroxide is needed to neutralise 0.05 moles of hydrogen sulfide? So we've got 0.05 moles of hydrogen sulfide. So first of all, we need to work out how many moles of sodium hydroxide will be needed to neutralise that amount. So it's a 2-to-1 ratio. So we need double the number of moles of sodium hydroxide. So 2 times 0.05 is 0.10 moles. So now we know the number of moles of sodium hydroxide. We need to work out the volume required if the concentration is 0.2 moles per decimeter cubed. So our equation, number of moles equals CV, concentration times volume. Rearrange that to find volume, so that's N over C, so that is 0.1 divided by 0.2, which is basically like 1 over 2, because again, if you're in trouble with the mental maths, a handy trick sometimes is just to multiply things up by a factor of 10. Multiply that up, it's 1, multiply that up, it's 2, 1 over 2 is 0.5. So that is 0.5, and look at answer B, the answer there says 0.5, but this is a very sneaky one because it's 0.5 decimeters cubed and it wants the answer in centimeters cubed. So they're being very, very sneaky here, considering you've had through a bit of mental maths to get to this stage and they've temptingly put one of those bits in there, but that's what they do. So to convert this to centimeters cubed, we need to multiply by 1000, so 0.5 times 1000 will be this one here then, 500 centimeters cubed. So we're going to go with D. Number 2 then, so we're combusting a hydrocarbon X. We don't know whether it's an alkene or an alkane or a cyclic alkane, and again it could be any, looking at these, because what we've got here, C4H6, well, that's definitely got some double bonds in it, because it's not even an alkene, because that would be C4H8, so it must have at least 2 double bonds, maybe a triple bond. Anywho, we'll get to that in just a second. So it's a combustion, and then what we've got then is if we've got a hydrocarbon, that's made up of carbon and hydrogen only. So if we sort of think, right, okay, if it's like, if we sort of say, right, it's CXHY, we don't know what those are yet, it's complete combustion, as it says there. So we're just going to get carbon dioxide and we're going to get water. And they've given us volumes of gases which are just like mole ratios basically. So if we get 15 centimeters cubed of this stuff reacting and it makes 60 centimeters cubed of carbon dioxide and 75 centimeters cubed of water, then as I say, these would be just like mole ratios. So that's basically a 4-to-1 ratio. Now, there's only one carbon dioxide per molecule, so if we have 4 times the amount of carbon dioxide in terms of the volume to the starting alkane, then we basically X equals 4. Okay, so we can rule out D already now. It's not going to be D because basically the carbons have to match up with this, and if it's a 4-to-1 ratio here, then we must be producing 4 CO2s from it. Say sort of, because if there were mole ratios, it would be sort of, if that was 60 moles and that was 15 moles, then there must be 4 times, well, it's been times by 4, so X is 4, whittling away, sorry. And then, okay, this is 5 times greater, so what we've got there is the water. Now there's 2 per molecule as well, remember. How would we get it where it's 5 times greater? Well, let's look at some of these ratios. Well, if it was 6, so if this was 6, then of course this would be 6 over 2, because this is how we get this. This is y over 2, and it's 5 times greater. So if this had been 6, then this would be free waters. It'd be 3 times bigger, and that would be 45. Pop into the next one. If this was 8, this would be 8 over 2, and then that would be 4, and 4 times 15, this would also be 60. So basically, this would be 45 waters. This would be 60 centimeters cubed waters. So it's looking promising for this one, because again, and the reason why I'm dividing by 2, of course, is there's 2 hydrogens per molecule. So if Y is 10, 10 divided by 2 is 5, and 75 is 5 times bigger than 15. So this is the answer that we want along here. The next one then, we've got 5 moles of iron oxide reacting with 6 moles of carbon monoxide. The reactant according to the equation below. What is the limiting reactant, and how many moles of the excess reactant remain unreacted? Well, a good trick that we do at GCSE, remember, is to sort of basically work out how many moles of one other product they can make, and whichever one can make the least is the limiting reactant. So if I've got 5 moles of iron oxide, how many moles of iron could that make? Well, that would be enough to make 10 moles, because it's a 2 to 1 ratio. And if I've got 6 moles of carbon monoxide, how many moles of iron is that enough to make? Well, it's a 3 to 2 ratio. So if this is 6 moles, then this must be kind of 2/3 of that, or I could divide this by 3 and then multiply by 2. So 6 divided by 3 is 2, times 2, it would be enough to make 4 moles. So the carbon monoxide can make the least amount of iron, so the carbon monoxide is the limiting reactant. So it's got to be one of those two. Coming to this bit then, okay, now we worked out carbon monoxide is limiting. 6 moles of carbon monoxide, we need to work out how many moles of iron oxide that would react with. Well, it's a 3 to 1 ratio. So if I've got 6 moles of carbon monoxide, I'm going to need 1/3 of that for the number of moles of iron oxide, which would be 2 moles reacting. 2 moles reacts, and I started with 5. So the amount left over at the end will be 3 moles. Okay, so again, they're trying to catch out here. 2 moles is the amount which reacts. There's 3 moles which is going to be left over and is in excess. So B is going to be our answer there. Coming on to number 4 then, so we've done the calculations bit, now we're on the atomic structure bit. So atomic structure, we've got our line spectrum. Now, one of the things you must always remember is that the lines converge, and by converge we mean get closer together at higher energy. So basically energy is going in that direction. Okay, so your energy is increasing in this direction. So here we got high energy, down this end. Which again, so like, okay, so that would be, this is the visible region, then this would be the violet end, because of course violet is next to ultraviolet, which is the high energy end. This end down here would be infrared. Don't need that for the purpose of this question, but again, it's just that familiar, and that's where you got infrared is less energy than visible, visible less energy than ultraviolet, and then of course we'd have the red down here, the violet down here. So we can see energies in one of these, 2 of these in fact, but there's also frequency and wavelength in there. So we also want to sort of figure out, okay, well, high energy, remember, is a high frequency. So frequency, this would also be a high frequency down this end, because frequency also increases as energy increases. So remember, high frequency forms of radiation like gamma rays are very damaging because they're very high energy. And then wavelength, remember, goes in the opposite direction. So what we would have here would be a small or a low wavelength. So small wavelength, because it goes in the opposite direction to these guys. Because as frequency increases, then wavelength decreases. So we've got a small wavelength down this side. So now we sort of set up our understanding of which way things are going here, the energy, the frequency, and the wavelength, the direction where they're increasing or decreasing. So line, let's run through the possibilities. Line M has a higher energy than line N. Well, that's not correct, so it's not that one, because energy increases that way. So M is actually lower energy than line N. Line N has a lower frequency than line M. Well, that's again incorrect because frequency is increasing in this direction. So N actually has a higher frequency than line M because frequency is increasing in this direction. Line M has a longer wavelength than line N. Well, that one makes sense because wavelength is decreasing in this direction, so M will have a larger or longer wavelength than line N, so that's looking like a good possibility. But again, it's always just good to rule them out if you have time. Lines converge at lower energy. Well, that's wrong. It's basically what set us up for this question at the start was remembering that lines converge at higher energy, so then we can assign the energy, the frequency, and the wavelength to this diagram. So C is going to be the right answer. On to number 5 then. So which representation would be correct for a species Z which has 31 protons, 40 neutrons and 28 electrons? So 31 protons is the atomic number, which would be the bottom left number. So I can quickly rule out these two where they put the number of electrons and they put the number of neutrons there. So it's got to be one of these. The number of neutrons isn't actually going to help me here because basically 31 plus 40 gives you the mass number, and they've got a mass number of 71. So it comes down to the number of electrons. One of them's got a positive charge, one's got a negative charge. So the atom, remember, would have also had 31 electrons to balance the number of protons. This has lost electrons, so it's a positive ion. We've got 3 more protons than we do electrons, so the positive protons win by 3 points. So that's the one that we want. Now we're into periodicity, so number 6, just bring in a bit more focus. Okay, I should have done that at the start, but that's a bit better. Still got the shadow and the cobra hanging above it. Never mind. So number 6, period-free element forms an oxide of the type M2O, which represents the first 4 successive ionization energies of M. Well, if you look at the formula, remember oxide is a 2- ion. And the fact that we've got 2 M's must they both have a 1+ charge. Okay, so the fact that we need 2 of them to balance out the 2- charge there means we're looking for a group 1 element. So remember the way we use these ionization energies is we're looking for the jumps in ionization energy. So here's where we've got the atom and we're taking 1 electron away, then 2, then a 3rd, and then a 4th one. So if it's group 1, we're looking for a big jump in ionization energy after we've taken the first electron, because then we're having to start a new electron shell. So here's A, so 496, that looks like quite a big jump up to there. That's about sort of 3,500 or so. And then obviously they increase because it becomes harder and harder to remove an electron, but that's not as big a jump as this one was. So this looks like my group 1 ionization energies. So I'm thinking A, but I'll just rule out the rest of them. This one here, then we go in reasonable big jump there. So this one looks like a group 2 element because we took 2 electrons from the outer shell and now we've had to start a new shell which is closer to the nucleus. 1, 2, 3, big jump there. So this one's a group 3. And then these are all fairly small, so this could be group 4, but we don't know. We haven't seen the jump. It could be a group 5 or a group 6, but it's certainly not a group 1 because we're not seeing a massive jump up here. So we're looking for number 6 to be A. Staying with periodicity then, so which property increases going down group 17, the halogens? Well, again, what can be handy is if you just kind of sketch kind of that periodic table and you sort of think, okay, we've got what increases left to right? Well, ionization energy increases, electron affinity increases, and electronegativity also increases. The only thing which doesn't increase going left to right, remember, the odd one out is atomic radius. Atomic radius decreases. And then going down, well, ionization energy, electron affinity, and electronegativity all decrease. And again, atomic structure is the odd one out. Atomic structure increases as you go down the group. And the reason for that is, as we go down the group, the atoms get bigger, so it's easier to remove an electron, harder to gain an electron, and they have less of an ability to attract a bonding pair of electrons. And obviously, as we add a new shell, the atomic radius gets bigger. Going left to right, nuclear charge increases, but we're not starting a new shell, so there's no increase in shielding. So your atomic radius decreases because the bigger nuclear charge pulls in the outer electrons more strongly. It's harder to remove an electron because they're being attracted by more protons. It's easier to gain an electron because, again, there'll be a greater attraction due to the higher nuclear charge, and they tend to sort of have a high ability to attract a bonding pair of electrons. Remember, fluorine is the most electronegative element that there is. So looking for our options here, so we've got electron affinity. So what increases going down group 17? Well, electron affinity, and this is true for any group, not just the halogens, going down a group, electron affinity decreases. It becomes harder to gain an electron as the atoms get bigger. Boiling point, well, going down the group here, we have chlorine, bromine and iodine. And these are simple molecules, don't forget. So simple molecules have just weak intermolecular forces, and these are also non-polar molecules such as F2, Cl2, Br2 and I2. So all they've got is London forces. Now remember, the bigger the molecule, the more electrons you have, and the more electrons you have, the more London forces you get, requiring more energy to break. And if we also think, well, fluorine and chlorine are both gases, bromine's a liquid, this is at room temperature, and iodine is a solid. So clearly boiling point increases as we go down the group because we go from a gas to two gases to a liquid to a solid. And as I say, it's because of the increase in strength or magnitude of the London forces. So that one's looking good. Let's just rule out the others. First, ionization energy, well, going down a group, doesn't matter what group it is, ionization energy decreases. It becomes easier to remove an electron. So it's not going to increase. And then reactivity, well, just remember fluorine is the Tyrannosaurus rex of the elements. There's nothing more reactive than fluorine, so it can only go down. And the reason for that is, remember that they're trying to gain electrons to get a full outer shell, and fluorine's a very small atom, so it will gain an electron very easily. It'll have a very high electron affinity, whereas iodine would be much less able to gain an electron, so it's going to be less reactive. So not that one, so I'm going to go with B. Number 8 then, which correctly describes the reaction between potassium and excess water. The reaction is endothermic. Well, no, it's not. It's very exothermic, the reaction. The final products of the reaction are potassium oxide and hydrogen. Well, we do get hydrogen gas, but not potassium oxide. And in fact, when it's in water, potassium oxide would immediately dissolve in the water and create potassium hydroxide anyway. So it's not this one. The final products of the reaction are potassium hydroxide and hydrogen, and that looks good to me. And then the final pH of the solution is 7. Well, there's a reason they call the alkali metals, and that's because the solution will be strongly alkaline at the end because of the presence of the potassium, well, the hydroxide ions that's making it alkaline. So that's wrong, so we're looking for C. Number 9, the oxidation state of cobalt in the complex ion, cobalt, ammonia, 5 ammonia ligands, bromine X is +3. Okay, so it's saying that the cobalt has got a free plus charge, sorry. Which of the following statements are correct? So the overall charge X here of the complex ion is 2+. Well, if the cobalt is 3+, 1, 2, 3, like that, ammonia, remember, is a neutral ligand, so that's not going to have any impact. Bromide has a 1- charge. So in combination, the bromide, the 1- charge is going to bring this down by 2. So that is going to be a 2+ charge, okay? Because it's 3+ for the cobalt. The bromide's got a 1-, so that's correct. The complex ion is octahedral. Well, there's 5, 6 ligands around it, so that's correct. They will arrange themselves in an octahedral fashion, where you'll have the cobalt, and then your ammonia's coming off. And let's put the bromine up here perhaps. And we have ammonia down here. And 2+. You might sort of think, oh, well, how did I know it was bromide there? To be honest, it could go at any one of these positions and it would be exactly the same molecule. It might not look like it, but these positions are all equivalent to each other. It's only if there were 2 bromines and 4 ammonias that then there could be 2 possibilities. I could either have them next to each other or right opposite each other. The cobalt-free ion is a half-filled D subshell. Well, let's get the periodic table. So if it's cobalt-free plus, here's cobalt, and it's 1, 2, 3, 4, 5, 6, 7, 1 along. Now remember, it's going to lose the 2 4s electrons first. That would be cobalt-2 plus, and then it's going to lose 1 more. So it would then be 1, 2, 3, 4, 5, 6. So it's going to have 6 D electrons when it's cobalt-free plus. So that is not the case, because it's basically, as I said, it's 4s2 and then cobalt, 3d, 1, 2, 3, 4, 5, and we said there was 7 in there, 1, 2, 3, 4, 5, 6 and 7. So when it goes to cobalt-free plus, we lose the 4s ones, and then so we lose those 2, that'll be empty, so it's not going to be 4s, and then your 3d will be 1, 2, 3, 4, 5, and then we've lost just 1 of those. So it's actually got 6 electrons in there, so it's not half filled. It would have to be cobalt-4 plus for it to be half filled. So we're going with 1 and 2 only. And then number 10 then, the last one on this little short video. What is the correct explanation for the colour of the hexa-aqua cuprate ion? So the copper with the 6 waters around it. So light is absorbed. That's what we're looking for, remember. It's not light being released, because that's where more the alkali metals, where they gain energy, and then when you heat them, for example, the metal ions, and then the electrons get excited into higher energy levels. As they fall back down, they release light at certain frequencies. That's not the case with transition metals, remember. What's going on here is a specific frequency of visible light is absorbed, and we see the other colours, which are not absorbed. So light is absorbed, so that's what we're looking for. We certainly don't want this one here, where light is released when an electron moves to a d orbital of higher energy. Well, no, that's not. So light is absorbed when an electron moves to a d orbital of higher energy. That sounds good to me. I'm quite liking that one, because visible light has been absorbed, and we get an electron, remember, where you got the splitting of the d sublevel, and if this was copper 2 plus, then basically we're popping an electron from there to there by absorbing a specific frequency of visible light, which would actually be orange light, and that's why we see the rest of the colours, which then add together to make blue. Light is absorbed when electrons move from the ligands to the central metal ion. Well, that's just a bit of nonsense. No, it's not the case. And then light is absorbed when electrons move between d and s orbitals. I suppose that's sort of saying here that what if the electrons were promoted from the d sublevel into the empty 4s perhaps. Well, again, that's not the case. It's d to d transitions, so A is our right answer. Okay. So that's the first video done.